Runfa, are you online?
Yeah, I'm here. Akshay, can you see me?
Yes.
Can you see me?
Could you start your screen share?
Yeah, sure. Uh, just a
So
second.
Runfa is going to talk about a new method, which at the time was state of the art on Cityscapes for semantic segmentation.
Just wait a moment.
Yeah, and it's a paper by really good researchers from Nvidia and University of Waterloo.
So, Akshay, can you see my screen? Akshay?
Yeah, I can see your screen. Start
Yeah.
when you're ready.
Okay. Wait. So let's get started. Good evening, everyone. I'm Renfa, and I'll be presenting the paper Gated-SCNN, Gated Shape CNNs for semantic segmentation, which is done by Nvidia and published on ICCV last year. I also attached the link to the project website and GitHub here. So this is the pipeline of my presentation. First, let me talk about something about the motivation for this work. So for semantic segmentation works, for most semantic segmentation works, all information like shape, colors, textures are all processed together inside a deep CNN. So this can lead to a problem like if one only wants to focus on the boundary of the object. So in this situation, high-level information like shape is more important than low-level information like color or texture. So to solve this problem, a potential solution is to incorporate additional connectivity, which can help the different types of information to flow across different scales of network depth. But this is not always effective and efficient. So if disentangling these representations by specific design, it can lead to a more natural and effective recognition pipeline. So this is actually also how GSCNN solved the problem. So let's take a quickly look at the structure of the GSCNN. So this is a new two-stream CNN architecture. And as you can see, GSCNN still maintain classical semantic segmentation CNN architecture as shown here. And but adding another shape stream module with a specific design gate mechanism to help the high-level activation in the classical CNN to gate the low-level activation in the shape stream to help it focus more on high-level information and deactivate noise and low-level information. So the objective of this paper is to accurately obtain semantic mask and sharper boundaries for especially small and thin objects. All right, so coming to the methodology, as you can see, there are three main components for this architecture: regular stream, shape stream, and fusion module. So as I said, the regular stream is just a standard semantic segmentation CNN, and the backbone can be changed. In this paper, it uses these three backbones. And shape stream is the most important, the core component for the whole structure. It takes the output from the regular stream as the input, and the M denotes the stride, and output this as the boundary map, which has the same size as the input image. So inside this shape stream, the most important part is this gated convolutional layer. So there are three gated convolutional layers in this shape stream. T denotes the index of the gate. ST is the boundaries from shape stream, and RT are features from regular stream. So first, we need to get an attention map, which can be done by first concatenate ST and RT, and then followed by 1x1 convolution, and then activated by a sigmoid function. And then GCL operation is by is an element-wise, first element-wise product ST and alpha T, and then add residual ST, and then channel-wise weighting with a kernel WT. So in the whole process, the most important part is this attention map. You can think of this alpha T as as an attention map, which gives more weights heavily for high-level shape information to help this shape stream to focus more on high-level information. So I've also attached the corresponding code. If you are interested, you can check it. So to better understand this, this is the output from the shape stream, the boundary map. And for the third module is the fusion module like this. And it takes the region features and shape features as the input to this ASPP module, attribute spatial pyramid pooling, which can preserve multi-scale contextual information. And I will talk about it later. For the output, it's the refined segmentation. And formally, it's in this form. So K denotes the number of classes. And intuitively, you can think of this as this output as the pixel-wise probability over all classes. So let me talk about this ASPP. So why is this ASPP? The reason is that for most semantic segmentation works, it requires the output to have the same size as the input. So, after a lot of convolutional layers, you have to enlarge your receptive field. So to upsampling, people always use FCN pooling layers, but this can lead to a problem like a loose resolution, and it's not learnable. So a good alternative is Atros, also called dilated convolution, which can reduce this loss resolution and is learnable. So let's quickly review this Atros convolution. So if kernel size is 3 and using dilated rate 2, you can see it actually operates on every 2 pixels, and you got the receptive field 7 cross 7. And this is the size of the receptive field can be computed using this equation, and still use the same kernel size 3, and with different dilated rates. You got different receptive field, and if you use dilated rate 4, it operates on every 4 pixels like this. So only use dilated convolution, it still has a problem because it cannot be used in multi-scale, the different scales. So in computer vision, there's a widely used method to solve multi-scale problem, the spatial pyramid approach. So ASPP is actually a combination of dilated convolution with spatial pyramid method. So ASPP in this paper still use exactly same as the previous work. So the dilated rate is still set to 6, 12, and 18 as the code showed, you can see. And the advantage of using this ASPP is to preserve multi-scale contextual information. So after talking about architecture, let's focus on loss. There are 3 losses used for training in this work. And HBC loss and segmentation loss are used for joint multitask learning. And BC loss is just a standard binary cross-entropy loss with respect to the semantic, the boundary map. And the C loss is a standard cross-entropy loss for with respect to the semantic features. So one thing should be noted is that you can see this HBC loss is computed before the S, the boundary map fed before fed into before this map fed into the fusion module. So this loss can actually update the parameters from both the regular stream and the shape stream. So by using this way, it jointly supervised segmentation and boundary map prediction. Okay, for dual task loss, it actually consists of 2 separate regularization laws. For the first loss, it's on boundary level. So to explain this loss, let me first explain this epsilon. So intuitively, epsilon, you can think of it as potential to indicate whether whether a particular pixel belongs to the semantic boundary as the input image. So to compute this epsilon, you take the spatial derivative to this guy, using Sobel or canny edge detector, whatever you want. This paper uses canny edge detector, and G denotes the Gaussian filter. Epsilon hat means the ground truth boundary pixels, which can be computed in the same way, especially except replacing this term with this semantic segmentation label. So P plus contains the set of all non-zero pixel coordinates from both the predicted boundary pixels and ground truth. So intuitively, this loss can first, when there's a mismatch with ground truth boundaries, predicted boundary pixels are penalized. And second, it can also avoid non-boundary pixels to dominate. And for second loss, it's on semantic level. So it's just, as you can see, it's just a standard cross-entropy loss with respect to the feature, the semantic features, and multiplied by an indicator function shown here. Okay, so let's talk about the experiment details. So the baseline is Deep Lab V3 Plus, also a state-of-the-art model. And dataset is the Cityscapes. 19 classes are used. For supervising the boundary, it does not use the coarse data from the Cityscapes 20,000 annotation. Because to supervise in boundary, it needs perfect ground truth. So it generates the ground truth boundaries using this existed method. So here lists some implementation details for training. And for testing, there are three metrics for metrics. And first, standard MIOU and F-score along boundaries, distance-based MIOU. First, for standard IOU, as you can see, GSCNN outperforms the baseline about 2%. And GSCNN also gets great improvements for small objects like motorcycle, traffic signs, traffic lights, and thinner objects like poles. So second metric is the boundary F-score. Typically, F-score is defined in this way, and beta denotes the relative importance between precision and recall. So in this paper, it still uses a previous defined F in a previous work shown here. So in this work, beta is set to 1, and the equation become like this way and like this, and a PC RC denotes contour-based precision and recall, respectively. So to compute this F-score, this paper used the slack and distance with different pixels and corresponding thresholds. So if your computed F-score is higher than this threshold, this pixel is deemed as correctly classified. So because there's no ground truth boundaries in testing data, so this part is done using validation set. So as you can see, the GSCNN outperforms the baseline about 4%. And for the third metric is the distance-based evaluation in terms of IOU. So the reason for using this metric is because the first metric we use, the global IOU metric, does not well reflect the accuracy for small objects. So to implement this, we need to first define a crop factor C and crop C pixels from the top and bottom and 2 C pixels from the left and right. So as you can see here, with greater crop factor, it focuses on more small and further objects. So here
there are 2 minutes left.
Oh, thank you, Bo. So as you can see in the right figure, it shows the comparison of distance-based evaluation of MIOU at different crop factors from 0 to 400. So clearly, GSCNN works better than the baseline. But another interesting fact is that with greater crop factor, GSCNN performs increasingly better than baseline. So the gap in performance between GSCNN and the baseline increases from about 2% here at crop factor 0 to close to 6% at crop factor 400. So this again proves that GSCNN performs better for small objects. So here's the comparison of errors in prediction. So first, let's see this figure using the baseline. You can see the red bars here are actually the gray poles in the ground truth. So these are misclassified as people. So it performs better in this GSCNN. So another thing is you can see this this figure. The red contour around the people is using GSCN is sharper than using baseline. So to help you guys better understand this, there's a very short demo video. This is the predicted semantic segmentation mask. Sorry. And this is the edges. And as you can see, using greater crop factor, oh, sorry. Oh, sorry. So as you can see, with using greater crop factors, it focuses on more smaller and further objects. So this is the output, the alpha channel of the image from the gate one. So you can see a lot of noises around the edges, and also you can see edges are mostly small and low level. And oh, sorry. And this is from gate 2. You can see the edges become thicker, and only object level, higher level edges are preserved. And you can also see here people in further area. So the objects, the further and smaller objects and thinner objects like poles shown here are all clearly segmented. And this is from gate 3. It's getting even better. Okay, so as for the advantages, GSCN produce sharper predictions around object boundaries and significantly boosts performance on thinner and smaller objects. And GSCN also can be easily incorporated into existing networks for performance improvements. As for the disadvantages, although GSCN is good work, but if you check the leaderboard on Cityscapes datasets, there are already 21 better works there, and 3 of them does not use the coarse data for training, just like this work. And the training scheme is also kind of complex. It uses 8 GPU to train. And it also needs to approximate gradients. So if you remember the laws, there's a step like this. So to backpropagate this argmax, you know, argmax is not differentiable. So for backpropagation, in this paper, it uses Gombo submax trick to solve it. So this is also a problem. And here are 3 takeaways. First, a new gating mechanism is derived to connect the intermediate layers, which deactivates low-level information and focus on high-level information. And second, to predict high-quality boundaries, a new loss function is derived to encourage the predicted semantic segmentation mask to align with ground truth boundaries. And last, GSCN achieves impressive performance on predicting small and thin objects. And here's my question for the class. What role does the GCL play for the GSCNN? And why use the distance-based MIOU as the metric? Thanks, and sorry for making this over time.
Very nice, Runfa. I like your slides. I also like watching little video that you had added.
Thank you, Professor.
Certainly seem to have enjoyed making this presentation.
Yeah.
You may want to, now that the presentation part is over, see if there is something in this one which might influence the way you and your team may want to do what you are doing for your project. I mean, I'm not saying there is a simple connection or anything, but see if there is something that might give you some idea or some thought regarding how do you measure performances and all that. But Akshay will definitely talk to you more with the group. But very nice. Thank you.
Thank you. Thank you, Professor.
Really good job, Runfa. You covered a
Akshay.
really dense paper, and I think broke down things to a very simple level. So there's quite a lot of questions. I'm trying to get to all of them. Let's see if I can do that. Okay, so the first question is from Keshav, who says, can you explain the flow of data from the regular stream to the shape stream?
Okay.
Sorry, yeah, go on.
Okay. Go ahead, sir.
Yeah.
Sorry.
Yeah, you can. Sorry.
Is that all the question?
No, the second statement is, are the outputs passed into each of the 1x1 convolutional layers?
Okay. So for the first question, let me explain how the information, the data from is from the regular stream to the shape stream. So see this slide. Actually, regular stream, there are 5 layers here shown in the paper, but if you refer to the code, you can find actually there are 7 layers. So they use the first layer, third layer, fourth layer, and the last layer for the input to the shape stream. And yeah, I think this kind of solved the first problem. And for the second problem, yes, after every gate convolutional layer, it adds a convolution, 1x1 convolution.
Okay, sounds good. Yeah, that's my understanding as well. So I'll get back to a few more questions from Keshav. Let me address a few questions from other people first. So we have a question from Srinidhi, who says, very interesting and neat presentation. She asks, can ASPP be replaced with UNets? As for having the same resolution as the input and for training the model in, it could be utilized, and even the receptive field could, due to pooling, can be improved by introducing holes in the kernels. So the question is, instead of this ASPP module here, could you just have another unit that basically processes the features even more and generates an output feature map instead of just pooling it from all these different scales? And you could get a large enough receptive field too.
For this question, so I don't understand. The key point is to concatenating the information or to upsampling. Her question?
Her question was, let's say you just concatenate the two outputs from the 2 streams, but after that, instead of using ASPP, can you just apply another neural network architecture like a UNet that would preserve the same feature size, but it would increase the receptive field? So instead of ASPP, could you have a small neural net at the end?
I'm actually not very sure about it, but I think if it plays the same role, I think it can be replaced. So ASPP actually, for ASPP, its main job is to do the spatial pyramid, like as I shown here. Where's that? So here, it actually achieves such tasks to specifically solve for spatial pyramid map problems. So did she mention UNet or something else? I don't know that.
Yeah, a UNet architecture is just something that reduces the spatial size of the feature map, and then once it's small enough, it then increases the spatial size again, so that you have you return back to the same original spatial size.
So
it's fine.
Think,
yeah.
Yes. So I think it can be replaced. It can be replaced here. So
yeah.
because
I agree.
Because here the essence to use the essence to use this thing is because if using a standard pooling layer, it's lose resolution. So if I'm not sure if that's UNet will have this problem, but I think if it doesn't, I think it's okay. So
UNet is another way to address this, I guess, an encoder-decoder pipeline. It has skip connections. So it has a bunch of downsampling layers in the beginning, and then you upsample them again. But there are skip connections connecting layers at the same resolution. So
so I think it's quite similar.
There are two, I guess, pretty popular approaches to dealing with this tension between having a larger receptive field and then high resolution.
So I wonder the later presentation, that one, the panoramic, I can't remember that. A panoramic pyramid spatial, is that also for this kind of thing?
That's for that's for semantic plus instance segmentation. But the point is, you could getting back to the original question, and I don't know how much time we have to just discuss this one. Is that you could potentially do it, but the whole point is that since they have this unique architecture, in semantic segmentation, you want to reduce the size as much as possible of the network, so have as many as few layers as possible, while increasing the receptive field drastically, because you're doing semantic level stuff. So since they've already done that, you don't necessarily need to have a unit after that. You could just do with something like ASPP, which is much more computationally effective.
And for that question, I have something else to say. So I did mention that this, so this shape stream is quite simple, as you can see. There are two other advantages of it. First, it operates on the same, from the start to the end, it operates on the same image resolution as the input image. This is quite a very simple structure. So
the way they describe it is the shape stream is a very shallow structure. So it has very small kernels.
Shallow architecture.
And it doesn't need a lot of operations to increase receptive field. Okay, so let's move on to the next question. It's from Hala. She says, very nice presentation. And she asks, why is it important to avoid non-boundary pixels in the loss function?
Non-boundary in the loss function. Sorry. Which one? Sorry, can you repeat the question?
The question is, why is it important to avoid non-boundary pixels in the loss function? I think it's the regularizer losses. These terms.
Oh, okay. So let me explain this again. So you can, as I said, you can think of this epsilon p plus as something to indicate whether the pixel belongs to the semantic boundary. So so there are two cases. So if this let me see how to explain this. So if how to explain this? So typically, if your predicted is matched to the ground truth, there's no penalty. But if there's a pixel at 100 100 in the ground truth, but there's no such pixel in 100 100 in the predicted boundary, so it will get a penalty. So I think.
I don't think that's the question. So you
Sorry.
So it's fine. And the top loss, right? So you mentioned your second bullet point. Do you see that? Avoid non-boundary pixels to dominate. So why is that? So what does that mean?
Sorry, can you?
So do you see the second? It's fine. Take your time. So do you see the second bullet point? Avoid non-boundary pixels to dominate that you have written down.
Yeah.
So so Hala's asking, what exactly does that mean? Yeah.
I think this is if there's if there's a wrong boundary pixel in the predicted image, there will be a penalty. So if this loss, if there's a wrong pixel, wrong prediction, it gets penalty. So it avoids the non-boundary pixels to dominate.
Yeah, that is right. But I guess, okay, to just add to what Runfa said, so the reason you don't want non-boundary pixels to dominate is usually in semantic segmentation, most networks, what happens is that it's very easy for these networks to classify non-boundary pixels. So if there's a pixel in the center of the car, it's quite easily classified as being a car. Whereas where it gets tricky is along the boundaries, because you don't want the non-boundary pixels to dominate the loss, because those are easier to classify things. You want the network to get to the harder to classify pixels, which are usually the boundary pixels. And this loss that you see at the top of the slide, the boundary level regularization, that specifically applies just to the boundaries. It doesn't apply a loss to the non-boundary points. So that's how you get very nice boundaries that sort of basically agree with the actual boundaries of the objects. Does that make sense, Runfa?
Sort of.
It's fine.
Thank you.
I guess thank you very much. A very nice presentation.
Thank you.
Okay, so the next question is from Sushrut, who asks, in general, do you think domain adaptation is needed for this model to work on different data sets? Because I think feature pyramid networks will take care of that.
Sorry, I'm not familiar with domain adaptation.
Oh, that's fine. Do you want to take a guess? It's fine. These questions are not necessarily part of the paper itself, but if you want to take a guess, you can.
Sorry, can you put that question in chat or
yeah, sure.
again? So, because
let me do that. So the question is that, so if you take this model, which has been trained on Cityscapes, right? Could you just apply it on any other data set, and is it going to work really well? Or do you have to sort of retrain it?
Take care of that. So yeah,
just to add,
yeah.
Sorry,
So for different situation, I think because I really don't, I'm not familiar with domain adaptation, so sorry, I can't guess.
That's fine. So actually, Shankwan had the exact same question. So in my experience, usually you do need some domain adaptation, or at least some fine tuning with ground truth data in your target domain, because it changes because you're doing pixel-wise classification and not necessarily just object detection. A lot of things change when you move to a different data set. Like you could have different color sciences for different camera sensors. You could have different exposures. Things could just appear different. So usually, if you won't get the same level of performance in a different data set, and there's a lot of work that just devoted to domain adaptation for semantic segmentation. So there's actually quite a few more questions. This seems to be a very popular presentation. So the next question is from Vishwas, who asks, gridding artifacts occur when dilated convolutions are used for semantic segmentation. Does the paper mention this, and any workaround for this? So I'm going to send this to you in the chat in case you want to. Yeah.
Maybe I overdid my encouragement of people making things lively, but this is beautiful.
Thank you, Professor.
Wonderful. It's very nice. And Akshay, if time is going to be an issue, we can continue this on Piazza also.
Yeah, sure. So we can make this the last question, and then other questions I can get to in the chat, or I can answer them on Piazza.
So this paper does not mention any workaround for this.
Yeah, that's actually right. This paper doesn't mention a workaround. But the reason I think it's not as big of an issue is because the shape stream, which you see here, like I said, it's a shallow network, so they don't downsample the image by a lot. So almost the entire image resolution is maintained by the shape stream. It's just the regular stream that gets downsampled quite a bit. So I would hope that that actually helps because you are retaining the resolution in the shape stream.
Okay.
Okay, so other questions I can answer, or I can put them to Runfa and then he can get back to us on the chat. But yeah, thanks Runfa, and
thank you.
Any other comments, Professor, or can we move on?
No, that's wonderful, wonderful presentation as well as very nice interaction. Thank you very much, everybody.
Thank you, Professor. So I just,
yeah.
Okay.
Could you stop your screen share? Do we have Sai Kiran online?
Yeah, I'm ready.
Yeah, you can start your screen share.